The Ford 335 engine family were a group of small block V8 engines built by the Ford Motor Company between 1970 and 1982. The significance of the numerals 335 designated to the series of Ford V8 engines come from Ford management, who dictated 335 cubic inches be the minimum capacity with room for expansion during its development. The series was nicknamed Cleveland after the Cleveland, Ohio engine plant in which most of these engines were manufactured, a plant complex in Brookpark, Ohio that included a gray iron foundry, a stamping plant, and an engine assembly plant. As newer automobile engines began incorporating aluminum blocks, Ford eventually closed the casting plant in May 2012. The 335 series engines were used in mid-sized and full-sized cars, as well as light trucks, at times concurrently with the larger member of the Windsor small block family, the 351 Windsor. These engines were also used as a replacement for the FE-V8 family in both the car and truck lines. The 335 series V8 engines, only outliving the FE by a half-decade, were eventually abandoned in favor of the more compact Windsor V8 engines. Overview: the 335 series V8 engines were introduced in late 1969 as the 351C. In the third quarter of 1970, the 400 was introduced to the passenger car lines, while the 351M replaced the 351C for the 1975 model year. Ford of Australia built the 351C engine beginning in November 1971, which was very similar to the American counterpart. Alongside the 351C, the 302C engine was produced, which was exclusive to the Australian market. The 335 series V8s were overhead valve pushrod V8 engines that used a short skirt engine block. This family of engines incorporated elements learned on the 385 big block series, particularly the poly-angle combustion chambers with canted valves, and thin wall casting technology. All 335 series V8s all had free-breathing large-port canted valve heads with a rugged engine block. The 335 engines use large main bearing caps, with 4-bolt attachment on some versions of the engines. All 335 series engines are cast with provisions for 4-bolt main bearing caps to be added through modification. The longer stroke of the 400 V8 required a taller deck height, and it used larger main bearings as compared to the 351C. This was similar to the changes required to make a 302 Windsor to the 351 Windsor. As a result, this engine family has two block deck heights, a low deck 9.206 in and a tall deck 10.297 in. Comparison to Ford Windsor V8 equals, all 335 series V8s shared the same 4.38 in bore spacing and cylinder head bolt pattern as the Ford Windsor V8 engines. Beyond these shared aspects, the 335 series engines are very different internally from the somewhat similar-looking Windsor series. The 335 series V8s use smaller 14mm spark plugs, and the radiator hose locations differ between the Windsor and 335 engines. The Windsor engines route coolant through the intake manifold, with the hose protruding horizontally, while the 335 engines had a dry manifold with a radiator hose connecting vertically to the cylinder block above the cam timing chain cover. The Cleveland has a square-shaped rocker cover, while the Windsor has a more rounded cover. All 335 covers are secured with 8 bolts. The Windsor uses 6 bolts. All of the 335 series engines differ from the Windsor engines by having approximately 2 inches extension at the front of the block, which forms an integrated timing cover casting. Oil system differences: as a method to reduce production costs, Ford eliminated one of the main oil galleys from the block casting, resulting in the 335 series to have 2 galleys versus the Windsor family's 3 galleys. The result was an oil system very similar to the 385 series V8 engines. The 2 main oil galleys in the 335 series engine run along the lifter bores. Oil is fed from the filter to the number 1 main bearing, followed by the number 1 cam bearing above. At the same time, it also feeds the right-hand oil galley, feeding the right side lifter bank. The lifter bank has 4 galleys that lead to each of the remaining main bearings. After the oil feeds the main bearings, it feeds each corresponding camshaft bearing above. At the rearmost main bearing, the oil goes into the other galley which feeds the left lifter bank. This system has proven to be adequate for street engines but can fall short in high rev race usage without modification. Cylinder heads. The cylinder head design for the 335 series engines is its most definitive aspect. All cylinder heads were two-valve heads, that use large ports with polyangle or canted valves. This resulted in the intake and exhaust valves being at separate angles. Canting the valves allowed for very large valves to be installed, while reducing the port length and minimizing sharp turns within the port. The end result was a cylinder head that had valves and ports much larger and freer flowing than the Ford Windsor V8s, and in some cases larger than some of the Ford FE and 385 series V8s. This same basic cylinder head design was used on the Ford Boss 302 engine, after it was modified to work with the Windsor engine block. Most 335 series engines use stamped rocker arms with cast fulcrums that made for a non-adjustable valve train. Only the Boss 351 and 351HO had adjustable valve train which had rocker arms mounted on screw-in studs and used guide plates. The 335 series engines used one of two different cylinder heads. The 4V head was used on engines equipped with a 4-barrel carburetor, while the 2V head was used with the engines equipped with 2-barrel carburetors. The 4V heads had larger ports and valves than the 2V, however, the 2V heads still had ports and valves that were significantly larger than Windsor engines. The 4V heads' large ports and valves were designed to promote better breathing at higher PM, while the smaller 2V ports have proven to be better for street use. The cylinder heads used either an open, almost shallow hemispherical-shaped combustion chamber or a closed quench-type combustion chamber. The closed chamber heads encloses the valves more closely, reducing the combustion chamber volume, but both combustion chambers designs have the same thermal efficiency and resistance to detonation. The closed combustion chamber promotes a better swelling action of the incoming air-fuel mixture, which provides a lower PM torque advantage over the open chamber. However, the open chamber cylinder heads exhibit better emissions characteristics. The other significant advantage to the closed chamber heads is that less machining is required to obtain high compression ratios. 351 Cleveland. History. Production of the 351 Windsor V8 engine began for the 1969 model year in the Windsor Engine Plant No. 1. Ford's sales and marketing forecast that the demand for this engine would exceed the plant's production capability, and it was decided the additional production would begin at the Cleveland engine plant. At this time it was also decided to upgrade the engine to a higher specification power plant. Two-cylinder head designs were developed to improve the 351W head. One cylinder head used the same basic design as the 351W, but with larger ports and valves. The other had canted intake and exhaust valves, similar to the Ford 385 series V8. Sales, marketing and product planning favored the canted valve design as it was viewed as more innovative. Other changes to the engine were related to ease of manufacture and improved reliability. This led to elimination of coolant flowing through the intake manifold to prevent unnecessary heat transfer. To perform this change, the front of the engine block was extended to include provisions for the coolant to flow through a crossover in the block. This extension also acted as an integrated timing chain housing. The timing chain housing was covered with flat steel that was easier to seal than the typical large timing chain cover used on other Ford V8s. These changes resulted in a bigger and heavier engine block than the Windsor V8s. The 351 Cleveland was not an all-new design but a development of the 351W into a higher performance variation. The 351 Cleveland was introduced in 1969 for the 1970 model year. Its actual displacement was 351.9 cubic inches. A 4V performance version and a 2V version were built. The 351C4V was marketed as a high-performance engine, featuring large valves, ports and a closed quench combustion chamber. Later versions of the 351C with 4 V-heads would continue to use the large ports and valves but would switch to open chamber heads in an effort to reduce engine emissions. The 351C2V was not marketed as a high-performance engine. It used the 2 V-cylinder heads with smaller valves, smaller ports, and open combustion chambers to produce a more economical engine that produced greater lower PM torque. Only the Q-code 351 Cobra Jet, R-code Boss 351, and R-code 351HO versions have 4 bolt mains bearing caps. H-code equals. The H-code 351 Cleveland engines are 2-barrel 351 CS with lower compression. Compression ratio ranged from 9.51 in 1970 to 8.01 in 1973 and 1974 and all years ran on regular grade fuel. All H-code 351s were equipped with a cast-iron crankshaft, 2 bolt main bearing caps, forged steel connecting rods, cast aluminum pistons, non-adjustable valve train and cast-iron intake and exhaust manifolds. All H-code 351 Cleveland engines used the 2 V-heads with smaller ports and had open combustion chambers. These engines were produced from 1970 through 1974 and were used on a variety of Ford models, from pony car to full size. The 351W with a 2 barrels carburetor was also produced during this time with the same horsepower rating, but Ford used the H-code to describe both engines. M-code equals. The M-code was a high-compression, high-performance variation of the 351C, produced in 1970 and 1971. The M-code engines used the large port 4 V-heads with a closed quench combustion chamber and large valves. These engines also included cast aluminum flat-top pistons, stiffer valve springs, a high-performance hydraulic camshaft, and a square-bore Autolite 4300A carburetor. The 1970 engines were 11.01 compression and produced 300 bhp at 5400 rpms, while 1971 versions had a slightly lower compression ratio of 10.7 to 1, and produced 285 bhp at 5400 rpms. The M-code 351C required premium fuel and was available in the 1970-71 Ford Torino, Mercury Montego, Ford Mustang and Mercury Cougar. 1971 R-code equals. The Boss 351 was the most potent high-performance variant of the 351C, available only in the 1971 Boss 351 Mustang. Rated at 330 bhp, it was fitted with a 4-barrel Autolite Model 4300D spreadbore carburetor, an aluminum intake manifold, solid lifters, dual-point distributor, a 6-quart oil pan and cast aluminum valve covers. Forged domed pistons gave an 11.31 nominal compression ratio, which made premium fuel necessary. It had 4 bolt main bearing caps selected for hardness and a premium cast iron crankshaft selected for hardness. The cylinder head was modified for better airflow, used screw-in studs with adjustable rocker arms, and except for the water passages were basically the same heads used on the Boss 300U. The valve train used hardened and ground push rods with guide plates, and single-groove hardened valve split locks. The forged connecting rods were shot-peened and monofluxed for strength, and used improved durability 180,000 psi 3/8 nuts and bolts. The R-code Boss 351 Mustang was only installed in the 1971 Boss 351 Ford Mustang, and it came equipped with ram air induction. Ford manufactured 1,806 Boss 351 Mustangs in 1971, 591 of which are registered and accounted for on the Boss 351 registry site. The January 2010 issue of Hot Rod magazine reported a project in which a Boss 351 was assembled to the exact internal specifications of an original motor, but fitted with open, long tube, 1-3/4 hooker headers, a facility water pump, a 750 Holly Street HP series carburetor, and minus the factory air filter assembly, engine accessories, or factory exhaust system. In that mildly modified state, it produced 383 horsepower gross HP at 6,100 rpms, and 391 lb-ft torque at 4,000 rpms. A measurement of SA net horsepower would be significantly lower, and represents a more realistic as-installed configuration with all engine accessories, air cleaner assembly, and automobile exhaust system. 1972 A code equals, the 351C HOA code had a number of changes to help meet emission standards for 1972 compared to the 1971 BOS 351 A code. The camshaft had less duration but more valve lift while the mechanical lifters remained unchanged. The forged pistons were changed to flat top style in the heads to open chamber heads but retained the same large ports, valves and adjustable valve train used in 1971. This resulted in a compression ratio decrease to 9.21 while the cleaner burning open chamber heads helped meet the new emissions regulations. The ram air option was no longer available. The engine otherwise remained unchanged from 1971. This engine produced 275 horsepower using the more realistic SAE net system and was only available in the 1972 Ford Mustang. Q code equals, the Q code 351 Cobra Jet version was produced from May 1971 through the 1974 model year. It was a lower compression design that included open chamber 4V heads. The open chamber heads exhibited superior emissions characteristics and were required to meet the more stringent emissions standards for 1972 and beyond. The 351 Cobra Jet high-performance engine that included a different intake manifold, high-lift long-duration camshaft with hydraulic valve lifters, different valve springs and dampers, a 750 CFM spread-bore 4300D motorcraft carburetor, dual-point distributor, and 4-bolt main bearing caps. These engines also featured induction-hardened exhaust seats for use with low-lead and unleaded gasoline. This engine was different from the 1970-71M Code 351C, having a more aggressive camshaft, a spread-bore carburetor, a 4-bolt block, and the lower compression allowed regular fuel to be used. It was rated a 280 bhp for all 1971 applications. For the 1972 model year, the only change to the engine was a retarding the camshaft events by 4 degrees. The engine was rated at 266 horsepower for 1972 when installed in the Mustang, and 248 horsepower in the Ford Torino and Mercury Montego. 1973 saw an increase in the combustion chamber size and the use of smaller valves, which reduced horsepower to 246 horsepower for the 4-barrel for the intermediate Fords, though it still retained the higher 266 horsepower rating in the Mustang. The 351CJ was rated at 255 horsepower in 1974 and was only installed in the Ford Ranchero, Ford Torino, Mercury Montego and the Mercury Cougar. Replacement equals, production of the 351C ended at the end of the 1974 model year. The engine was replaced by the 351M for the 1975 model year. This new variation used the same bore and stroke dimensions of the 351C but used the tall deck block from the 400 V8 engine. 351C engine specifications chart equals 400 and 351M 400 equals, by 1970 the 390 V8 FE engine was becoming outdated. With pending emission requirements, a more modern replacement was needed. Although the big block 385 family was used to replace the larger displacement 428 V8 FE engine, this engine family had nothing comparable in size to the 390 V8. For the 1971 model year, Ford introduced the 400 V8 engine as a replacement for the 390 V8. Ford billed the 400 as the 351C's big brother. It was designed to provide brisk acceleration in medium to heavyweight vehicles in an engine package that was smaller and lighter than the FE V8 engines and the 385 series Ford V8s. The Ford 400 engine was based on the 351 Cleveland. It had a half-inch longer stroke than the 351 Cleveland, making it the longest stroke Ford pushrod V8 engine. The 400 had square proportions, with a 4.0-in bore and stroke. Ford called the engine 400 cubic inches but it actually displaced 402 cubic inches, making it the largest displacement small block V8 made at that time. The longer stroke required Ford to increase the block deck height to 10.297 inches compared to the 351C's 9.206 inches. As a result, the 400 used longer connecting rods than the 351C, but it retained the same connecting rod-to-stroke ratio as the 351C. The 400 featured larger 3.00-inch main bearing journals, the same size as those used in the 351 Windsor, but rod journals were the same size as the 351C. The cylinder heads for the 400 were the same as those used on the 351C2V, having the open combustion chamber with smaller 2V-sized ports and valves. The 400 was only ever produced with a two-barrel carburetor, a cast-iron intake manifold, and the smaller port 2V cylinder heads. The 400 was designed as a high-torque, lower PM engine that was a smaller, more efficient and lighter alternative for the big Ford 385 engines, the 429 and 460, for use in Ford's medium and large-size cars. Weighing just 80% of a similar big block, it was originally available in Ford's Custom, Galaxy and Limited lines, and in Mercury Monterey, Marquis, and Brougham for the 1971 model year. For 1972, it was also available in the Ford Torino, Mercury Montego and its variations through 1979. By the late 1970s it was also available in the Ford Thunderbird, Ford F-Series pickup trucks, the Lincoln Continental, and Mark V. Unlike the 351C, almost all 400 blocks used the large bell housing bolt pattern used by the 385 family big block and were typically equipped with the higher torque capacity C6 transmission. There were a small number of 400 block castings produced in 1973 with the dual bell housing patterns. It had the large bell housing and the small bell housing bolt pattern used by the Windsor V8 family and the 351C, though it was not necessarily drilled for both. These particular blocks have been dubbed the 400 FMX by enthusiasts, though were never officially referenced as such by Ford. Most 400s also had unique engine mount bolt pattern, but these 400 FMX blocks had provisions for both 351C style and 400 351st engine mounts. For 1972, the compression was reduced through the use of dished pistons. The compression reduced again for 1973 and a new timing set retarded the camshaft timing 6 a degree to aid with reducing emissions. Changes to the cylinder heads for 1975 to add the Wehrmachter emission system caused the exhaust port to be more restrictive than the earlier 1971-74 heads. The 400 was retuned by Ford in 1975 to use unleaded gasoline with the addition of catalytic converters to the exhaust system. The development of the 400 V8 led to a significant design flaw that remained with the engine throughout its production life. With a longer stroke, the compression ratio became excessively high with the 351-2V heads and flat-top pistons. Ford engineers reduced the compression ratio by using a piston with a compression height that was too short, and this led to an excessive deck clearance of 0.067 inches compared to a 351-2V at 0.035. In 1971, this method of reducing compression was sufficient due to the higher octane leaded fuels. However, once lower octane unleaded fuels became used, the excessive deck clearance led to problems with detonation. For 1975, Ford dealt with this problem by decreasing the compression ratio further with a larger 15 cc piston dish and reducing ignition timing. However, the 400 V8 obtained a reputation for being prone to detonation. Although Ford did not make a piston to correct this, Tamiya Incorporated worked with Keith Black Pistons to make a 400 piston that increases the compression ratio and gives the piston a zero deck clearance. 351 meters equals, when the 351 Cleveland was discontinued after the 1974 model year, Ford needed another engine in that size range, since production of the 351 Windsor was not sufficient. Ford took the 400 engine's tall deck block and stroked it with a shorter 3.5-inch stroke crankshaft to produce a 351 cubic inch engine. This crankshaft was not the same as a 351C, in that it used the larger 3.0-in main bearing journals of the 400 V8. To compensate for the shorter stroke, the pistons for the 351M have a taller compression height, so that it could use the same connecting rods as the 400. The result of the 351M using the longer 400 connecting rod was a poorer connecting rod-to-stroke ratio than the 351C and 400. Other than pistons and crankshaft, the 351M shared all of its major components with the 400, and it also used the large 385 series style bell housing. The 351M was only ever equipped with a 2-barrel carburetor and open-chamber small-port 2V cylinder heads. 351M production began for the 1975 model year and blocks were cast in the Michigan Casting Center or the Cleveland Foundry. The 351M was the last pushrod V8 block designed by Ford. Light truck usage equals, for the 1977 model year, Ford replaced its FE big block 360 and 390 engines in its light truck line with its new 351M and 400 engines. For light truck use, a manual transmission could be ordered for the first time with these engines. As a result, the block was strengthened in the main bearing supports, in particular the number 3 support to better handle the loads imparted by the clutch. The truck engines had unique parts including pistons for different compression ratios from the car engines, truck-specific intake and exhaust manifolds, camshaft with more lift, and timing set that did not retard the camshaft timing. The strengthened engine block was introduced to the Ford cars for the 1978 model year. Block cracking problems the 400 V8s for the model years 1971 and Euro 72 were either cast in the Dearborn Iron Foundry or the Cleveland Foundry. Those built for model years 1973 and Euro 79 were either cast in the Cleveland Foundry or the Michigan Casting Center. The 351M introduced in 1975 shared the same block as the 400. The 351M and 400 blocks cast at the Michigan Casting Center prior to March 2, 1977 experienced water jacket cracking problems above the lifter bores. The cracking was caused by an internal coring problem when the blocks were cast. The result was horizontal cracks approximately 1 inch above the lifter bore. After March 2, 1977 the blocks cast at Michigan Casting Center did not have problems with cracking. 351M/400 naming convention confusion there exists debate as to what Ford intended the M designation of the 351M to refer to. Some claim the M stands for a Euro OE modified, a Euro being modified from a 400 V8 with a shortened stroke, though others claim that the M refers to the Michigan Casting Center, where the 351M began production. There is also some who say that the M designation has no official meaning, and it was just Ford's way of distinguishing the 351M for the 351C and 351W. Likewise, Ford's use of the 400 block in the creation of the 351M engine has resulted in the 400 mistakenly being referred to as the 400M, or 400 modified. This is despite the 400 having been the design basis from which the modified 351M was derived, and it was in production several years before Ford used the M designation. Further confusion arises from Ford printing 351M/400 on the emission stickers for the engine. The 351M/400 reference the engine family, but it may be confused as the engine name. Ford's official name for the 400 V8 contains no additional designations, the proper nomenclature is simply 400. Replacement the 351M and 400 were last offered in a Ford passenger car in 1979. They remained available in Ford light trucks until 1982. Reduced demand for larger engines due to tightening CAFE regulations led to the abandonment of the 351M/400 and the Cleveland production line. By 1980, mid-sized V8s had disappeared from the option list for almost all Ford cars. Only the full-size Panther platform Fords had anything larger than 302 Si available, and this need was filled with the 351W. With low demand for engines in the size range of the 351M/400, the 335 series V8s no longer had a need to be produced. In addition, there were difficulties adapting the M block to the second generation of emissions controls. Unlike previous Ford engines, Wehrmacht and exhaust gas recirculation features had already been built into the 351M and 400 engine, rendering adaptation to electronic feedback fuel air systems difficult. One requirement of the second-generation equipment was an oxygen sensor in the exhaust, which had to be placed before the Wehrmacht air was added. Since Wehrmacht air was injected right into the block's exhaust ports in the M block, there was nowhere for the O2 sensor to go. 302 and 351 Cleveland. Note that there was also a 302 Windsor. History During the 1969 model year, Ford of Australia imported approximately 17,302 Windsor and 351 Windsor V8s. However, the 351 Windsor was phased out for 1970 in favor of the newer 351 Cleveland. The 351 Cleveland engines continued to be imported from the U.S. along with the 302 Windsor V8. Both the low-performance 351C2V and the high-performance 351C4V were imported, with the vast majority of the engines being the 351C2V. Like the U.S. engines, the 4V versions used the closed quench-chambered heads and used the larger ports on the cylinder heads. In November 1971, Ford of Australia began to manufacture the 335 series V8 locally. He produced the 351C2V engine along with a short-stroke version displacing 302 cubic inches. These new locally built engines replaced the previously imported 302 Windsor and 351C from the USA. Initially, the cylinder blocks were still imported from the USA, while the remaining parts were manufactured in Australia at the Geelong Ford foundry. In March 1972, production of the 351C4V began in Geelong. In 1973, Ford of Australia received word of the fact the Ford of USA was stopping production of the 351 Cleveland engine after the 1974 model year. As a result, Ford of Australia placed an order for approximately 60,000 engine blocks to act as a supply until Geelong could start producing its own engine blocks. In 1975, Geelong began production of its own engine blocks, which had continued until December of 1981. All engine blocks produced in Australia were the short deck 9.206 inches engine block. The last Australian Ford to receive a Cleveland V8 engine was a Ford XE Fairmont Guy ESP sedan, vehicle identification number JG32 Arkansas, 33633K, built on November 25, 1982. Ford Australia continued to make remnant stock of the 351C available in Bronco and F-Series vehicles until August 1985. Australian-built 351 engines were also used by De Tomaso in Italy for the Pantra, Longchamp, and Deauville cars after American supplies had come to an end. These engines were tuned in Switzerland and were available with a range of outputs up to 360 picoseconds. 302 Cleveland In November 1971, Ford of Australia began to manufacture the 302 cubic inches Cleveland engine at the Geelong engine plant alongside of the 351C. The engine remained in production until 1982 and was only produced in Australia. The 302C was considered an economy V8, and it is estimated that only 10% of Australian Cleveland 5.8 production was the 302C. The 302C was created by using the 351C block with a crankshaft that had a 3.0-inch stroke, while it shared the 2.75 inches main journal size of the 351C. The 302C had a 6.020-in connecting rod to allow it to share the same piston as the 351C. This resulted in a connecting rod-to-stroke ratio of 2.01 to 1, the least desirable of any of the 335 series V8s. The 302C used a unique cylinder head compared to the Australian 351C to ensure an adequate compression ratio. The 302C had used the quench-closed combustion chamber with a volume of 56.4 Euro 59.4 cc's, the smallest of any 335 series engine cylinder head. This head used the small 2V ports and valves, making it the only 335 series head with the closed chambers and small 2V ports. The combination of the closed chamber heads with the small 2V ports has caused the 302C head to be a bolt-on performance upgrade for other 335 series V8s. Having the smallest combustion chamber of the 335 series V8s, these cylinder heads will easily boost the static compression ratio of any other 335 series V8. In addition, the small ports used on these heads are more efficient for a street performance engine than the large port 4V heads that tend to favor performance only at higher engine speeds. 351 Cleveland until production of the 351 Cleveland began in Australia for 1972, the 351C was imported from the US. Both the 351-2V and 351-4V were imported and were in all respects the same as the American counterparts. In November 1971, when Ford of Australia began producing its own engines, it only produced one style of cylinder head for the 351 engine. This was the 2V head with the smaller ports and open-chamber cylinder heads. In March 1972, Ford of Australia began offered a new 351-4V engine with a 4-barrel carburetor. However, these engines used the same 2V cylinder heads as the 351-2V, with a unique intake manifold. No 351C built in Australia used the large port cylinder heads or closed-chamber combustion chambers like the US-built 351C 4V engines. See also, Ford 385 engine, list of Ford engines. References External links, short descriptions of Ford overhead valve V8 engines, M-Block Ford V8 workshop.